Um, so welcome everyone. Um, I hope we are live right now. Yes, I think we are. So once again, welcome everyone uh, to our joint meetup of JugWro and Wrocław JAG communities. Sorry. Today we are welcome our guest Vaughn Vernon. Thank you, Vaughn, for accepting our invitation. It's great to have you here. Before we jump into the presentation, let's briefly discuss a little bit organization topics. Like the question and answers will be at the end of our presentations. Question can be asked on YouTube chat. For most active user, there will be a reward in form of IntelliJ license. That's about it about the organization matter. Now I'm gonna handing microphone to you, Vaughn. Go ahead.
Thank you, Patrick and Sebastian, for setting this up and making it possible. I just wanted to mention that this was actually planned for sometime in June 2020, but I was going to attend and speak at and I think teach at the Greenfield conference up in, is it Poznan? Well, we all know what happened. I was supposed to travel down to this meetup in June, but it's been delayed a long time. And of course, we're now finding ways to get back on track, even though we can't be together. So I do hope that someday soon, I can actually visit you in person live, and that would be a great honor for me and privilege. And so let's hope that we can get together sometime soon. I wanted to talk today about reactive domain-driven design with message streaming. So you probably have heard of reactive programming. Maybe some of you have been using reactive in one form or another. I want to be clear, this does not mean React.js or responsive UIs. That, of course, is a thing and could be counted among reactive programming. But this topic is really about, I guess you would say, server side. So how can you use message streaming in the actual server side application or microservice? I'll be explaining then in order what these things are and how they can be used. So reactive and domain-driven design and message streaming, and then how they fit together. Okay, so first of all, it's probably a good idea to start with what comes from the Reactive Manifesto. And the Reactive Manifesto describes reactive in this way. Reactive is message-driven. Okay. And in being message-driven, there are actually four total reactive characteristics or properties that we're interested in, but this one kind of is a foundation for the other three. So it's quite important to understand this. So let's go to have a color for this. We're going to call this message driven. And what message driven means is we're not going to create objects that, like in Java. Okay, this is the Jug or the Java user group. So let's use this in context. So in Java, you may have object A and object B. And if A wants B to do something, it invokes a method on B. And the method invocation is very much a blocking operation. So if we tell B to do something, B will take control of that, and A will block until B is done. And of course, there could be an entire call graph or method invocation graph on this side. And so A might block for, relatively speaking, a long time. So do something is handled. The reason for that is do something is handled on the same thread. So B takes over the thread of operation, and thus A cannot do anything until B is finished. Okay, we could actually refer to do something as a message. So you could, instead of speaking of do something as a method invocation, if you go way back to the beginning of object-oriented, and I'm talking one step further than Simula, and that's with Smalltalk and Alan Kay's vision for object-oriented and what that really meant. Alan Kay meant for object-oriented to be primarily implemented around message sending. And so you could do what it appears to be here to be a method invocation in Java, but initially object-oriented was never meant to use method invocations object to object. It was really object sends a message to another object, and the name of that message would be used to look up the actual method in a class dictionary for B, whatever type B is. And when it looked up, this message that's sent is actually called a message selector, and it's the pattern of the message. And so that selector is used as a key to look up in a dictionary or a hash map what the actual method is for that. And then the method is invoked behind this. The method doesn't actually happen initially. Now, you could say that do something is a message that is being sent, and the compiler is compiling out that lookup, right? So there's an optimization built into the compiler that says you don't have to look in a V table now to find this. Instead, what we're going to do is we know that you are invoking intending to invoke the do something method on B directly. Therefore, we will compile out the overhead of that table that, message dictionary. And so we're just going to actually invoke that method. But I like to still think of this as message sending because it really gets back to the roots of object-oriented. So pronounce this as you like, or say it like as you wish to, but I think it's important to think of objects sending message to one another. Still, in Smalltalk, back in, when Smalltalk first arrived, sort of somewhat, not publicly, but at least in research centers, around 1972, Smalltalk 72 was sort of the first one to see light outside of Xerox PARC. And with that, the message sending was still blocking. So this is a roundabout way of explaining that message driven does not absolutely mean non-blocking. And so technically speaking, we could say that message driven includes any kind of message sending, which means a message that is reified into some way to invoke a method elsewhere. But for the sake of the reactive manifesto, we're going to say that message driven within reactive is asynchronous. Okay. And by asynchronous, this means that there is a separate context to the message sender than there is to the message receiver. That doesn't mean necessarily either that you have enough threads to make the message be delivered very promptly on a thread to the receiver, because it could be that there are too few threads, actual physical OS threads available to perform that operation sort of very close to immediately. Therefore, asynchronous means that at least the sender and the receiver will have two contexts. One is sending the message, and there is a separate context for receiving and handling the message. In fact, if you had a single threaded process that could only use one thread, it would be the same thread that object A sent the message on that would eventually deliver the message to object B, because you would need some sort of thread task switching between them. Okay, but for the sake of, pardon me, most modern programming, we're going to have to say that it's meant to be asynchronous, which therefore also means concurrent, because we're assuming that we have multiple threads to run multiple, deliver multiple messages on simultaneously. And we also have to think in terms of that because of it being concurrent, there will also be parallelism, where two threads will actually be doing two different things, completely different things at the same time. So just to kind of clarify that, all right? So another important property of message-driven, and it becomes more obvious why message-driven is important to reactive, and this is responsiveness. So within the reactive manifesto, reactive microservices or applications or entire systems are meant to be responsive, and the responsiveness is driven by the asynchronous message sending, the message-driven part of this. So by sending messages, any incoming requests to this application, let's say, or let's just say microservice for the sake of argument. Let me move this out of the way a little bit. So we can think of a user, Julia is out here, and Julia has, through HTTP, sent a message to our application or microservice. And when Julia does that, maybe there are thousands, even millions of other users sending messages over HTTP constantly. And so how do we continue to respond to those? So first of all, disconnecting the thread between this operation where the client sends through a browser a message, it's important to disconnect that thread on our side that starts handling that incoming request from the rest of the application underneath it. And those components that are running underneath it in the domain model, let's say, are completely separated from those that are handling the request. And when the request sends a message, when the request handler sends a message to the domain model, that thread now becomes available to other parts of the microservice until the domain model completes, and then the request handler will provide a response to Julia based on the outcome of what happened in the internal part of this. And I just want to make clear too that it may not be obvious to you, but when you look up in the HTTP spec, the HTTP spec talks about every single HTTP request and response as messages. So in case you were unaware, HTTP is a messaging protocol. So message-driven is actually part of the HTTP spec. Go look it up if you're unfamiliar with that. And so we can actually say that even at the UI level and at some integration levels where we're sending integration requests and getting responses based on HTTP, those are also message-driven. And the fact that when we receive an HTTP request at the top level, we are, we are disconnecting the request handler, request receiver from the rest of the application. And so our side at a minimum is asynchronous and non-blocking even at the entry point to this application. Now, I don't mean to say that the only responsiveness about the microservice is at the UI. Of course, it's responsive in every direction, and we could say that there are also incoming, messages from other things, like a message broker, could be the thing that's sending a message in. And so this is also responsive and not blocking. So let's call this a broker or a bus. Okay. So this is a broker or a bus. It's not a human user, but this still must be responsive. Okay. So this responsive doesn't relate entirely to the outside. It also applies to the inside, but it was convenient to use that. Okay, but how do we remain responsive as users grow from thousands to tens of thousands to hundreds of thousands to millions and maybe even many tens of millions? Well, we have to provide another property or characteristic, and this one we're going to call elastic. So elastic is also made possible by message-driven, and elastic also makes responsiveness possible over varying circumstances. Okay, so you might think of that we have a single finite set of servers that are running our microservice or application on the server side, but with reactive, we actually have the ability to scale out and even potentially scale up depending on how the scale out works. So as we scale out, we could also have more powerful servers that are used in the scale out. But let's just say scale out, and we just add more server instances, and these can even be within a cluster. And the importance of the cluster part of it, or the grid part of it, is that the message sending now is transparently echoed. So if that message is received at some location in our microservice, and we now need to ask some other component in our microservice or application that's scaled, then that message can be relayed through the cluster without any sort of knowledge of that from the sender of that message. So for example, if we have an HTTP request handler up here, and that request handler says, oh, this needs to be delegated or dispatched to some actor in the domain model, some entity in the domain model, then it can dispatch that, in the sense that it's completely opaque to this web tier or web component, because we just send a message and the cluster figures out where that message should be routed for us, or the grid on top of the cluster. Okay, and then when load starts to decrease, so load has increased and caused an elastic growth toward outward increase, now we can stack in when load starts to decrease. Okay, so let's talk about the fourth property characteristic, quite important, and is called resilient. And resilient means that that if a crash may happen in some component, that single component will not take down a large part of, if not the entire microservice or application. So this means that the microservice or application as a whole can continue to be responsive, because even in the face of some failure deep inside the microservice, that failure will not bubble up as it typically would with this kind of, what we would typically find, for example, like in Spring Boot, where you go some number of calls deep into the system, and what actually happens in that case? Well, you keep invoking methods directly, right? You keep just invoking methods on, and you reach Z back here, Z, and Z has some kind of problem, and it throws an exception. What happens? Well, you know exactly what happens. So there's a lot going on between here and there, and realistically, no component object from here back knows what to do about that. It's just not a specialized in taking care of those problems. So say that there's a failure in the database that happens, way out here, and say this component here just says, oh, well, there's a problem with the database. And it may wrap the initial cause, the original cause of that exception in another exception and make it more application friendly, but that's going to get thrown, and all the way back through this call stack, it's just going to be, hopefully, we all wish for runtime exceptions because we don't know what to do with them. And finally, it ends up where? It ends up in the UI at best, right? Or we give some really meaningful message, such as, something went wrong, that component or part of the service is not available right now. So try again later, right? Or worst case, in this situation of the UI, it just shows up on their UI, a stack trace, and they're like, what in the world is that? You know, because nobody knew what to do with that. On the other hand, in a reactive message-driven scenario, when a component crashes, and I'm going to draw my components as circles now to illustrate a point that I'm talking about a reactive component rather than a typical blocking component. So let's say that, you know, A uses B again, and we get all the way back to Z, and something goes wrong with Z, right? So we have a crash here. Let's do a nice crash symbol here. So Z crashes. B, A, and everything in between Z and B don't have to know about this, because the message sending or the message driven characteristic or property of reactive naturally brings about the ability to have what are called supervisors. So we're going to have a supervisor here. And that supervisor knows how to do something about this failure, and it could do a number of things. It could tell the Z object to stay operational, but refuse new messages gracefully until further notice. And that could be done because the supervisor has the ability to ping the database and sort of find out, is the database alive? If it's not alive, if we've lost our connection, then the supervisor can arrange for a reconnection to occur on some sort of back-off retry schedule. And then once a connection is available again, we can send a message to Z and tell Z to go active again, and that crash is effectively done away with, and now the path is open again for Z to talk to the database. So these kinds of failure hotspots are important to recognize in the design of your code, and you have to plan for that. But even if you don't plan for it at all the right places, the default supervisors that are built in to a fundamentally useful reactive system, let's say platform or SDK, those are still going to prevent the cascading failure. So Z will never throw an exception back to here, even if it doesn't have a specialized supervisor. It will still have what's known as a default supervisor, and that supervisor will prevent cascading failure. So, this is a good thing. And any failures that may be caused anywhere up the chain or stack, it's not even a stack, the message sending route will still be protected from those kinds of situations. Okay, so you get an idea of what reactive is. Now let's go to Excalidraw again, and I'm going to start from a different perspective, and that is what is domain-driven design. So domain-driven design uses as a very, again, fundamental part of domain-driven design is what is called the bounded context. And the bounded context is a place where a model has relevance, where it has meaning, and that is because inside the bounded context, we model software that follows what's called or reflects what's called the ubiquitous language. So the ubiquitous language is modeled inside the context, and it's actually this outer boundary. Let's give it a little bit thicker line just to make a point that it's this outer boundary that says everything within this boundary adheres to our ubiquitous language and has the definitions that we give to our model. So whatever the concepts are inside this, those are pure in the sense that they are typically not polluted or corrupted by any outside concepts or naming or meanings, because inside this context, even things that have names that are familiar outside will not necessarily apply inside, because we have a specific meaning for those things, for those concepts. And then, because domain-driven design, partitions the whole system into different bounded contexts, because we have such a sort of minimal definition of what a language is here, then we're going to need a different ubiquitous language in different contexts. And those different languages in different contexts represent different conversations. And where do these conversations, how do they come about? Well, we have a number of developers and what are called domain experts in domain-driven design, or subject matter experts, if you will. And these individuals work on a team together, and they decide what the ubiquitous language means in their context. And those meanings and so forth will be different than the meanings of these in this context. And say that the team over here is different than this team entirely, but it could be that the same domain expert who works on this team also works on this team. It's just that they are carrying in a different context and language and meaning when they're working in this context over here. So it's important to understand that division. Okay, now where does the reactive, let me just draw one more thing. Very likely you also have one of these situations, what's called a big ball of mud. And I think most of us often work in and around legacy systems. And if we aren't working in a legacy system, we're probably at least working with it in the sense that we have to integrate with it. And so, we get these situations now where there are so many different kinds of objects entangled with one another, and so many dependencies that are nearly impossible to decipher without a lot of effort and study of the system. And so we can just keep, repeating this, not quite endlessly, but what seems to be endlessly sometimes, where you just get this mud going, and who can make sense of that? So so we often, with a new bounded context, have to integrate with legacy like this, and therefore, we have to deal with the fact that this situation exists. And I will explain as we get into the reactive DDD together, to explain how this works. So fundamentally, domain-driven design is yes, driving this kind of contextual situation here that causes multiple ubiquitous languages and even tangled implicit languages that no one can really see definitely where a ubiquitous language, begins here and ends within this. It's just so much tangle that you just have to kind of say, well, there are probably 10 or 12 number of subdomains within this, which could represent ubiquitous languages in a context if they had been implemented with domain-driven design, but they haven't. Okay, so that's what we get into this situation. So I'm going to go to yet another Excalidraw drawing here. And we're going to clear this one. Yeah. So now, what is reactive DDD? Well, reactive DDD is obviously combining the idea of bounded context with reactive. So you can expect, oops, let's see here. There we go. We can expect that two new bounded contexts aren't going to use those blocking types of objects that we were seeing in this model. Okay, so again, I'm representing normal objects, like objects that we would think of in Java as, sort of, I would say, contemporary objects as being these rectangles, whereas I'm going to draw these as circles in a reactive DDD setting, just to distinguish them. And so we have, let's say, the same two bounded contexts, but they're now implemented internally in a different way. And that different way includes how the domain model and all surrounding parts of this, even boundary objects, adapters and imports and adapters architecture, these are still message-driven, non-blocking objects, okay? And the same goes for this context. We have boundary objects that are provided here. And of course, we have our team on each side. Okay. So let's just grab this again, and let's paste it over here. So we really have, get that. We really have a very similar, I'm going to have to get rid of this. a very similar situation on the other side, but the insides of this context and at the edges, at the boundaries, the adapters are also non-blocking. Okay, but we still face the blocking big ball of mud. And so how we integrate with that big ball of mud, for example, through this reactive component here, whoops, through this reactive component here, and this reactive component here, we integrate with the big ball of mud. So how is it that we prevent blocking here? Because these are supposed to be asynchronous, and maybe we have to make a REST or a SOAP request, or maybe even Corba, going way back, could even still have to integrate with a Corba legacy system. How do we prevent that from being a blocking operation to this object right here and to that object right there, where basically they are going to park a thread, and which means it won't be available as long as this is required. And you know what's going to happen in the legacy? It's going to be slow. So how do we prevent having this disconnection occur in this case? Okay, a couple of ways to do that. First of all, if we are using HTTP, we can have an HTTP client that is non-blocking. So what happens is this non-blocking HTTP client knows how to send an HTTP request message and release the thread while this occurs. And there is a listener to all responses that again is non-blocking, but that listener is basically polling on our side periodically on a time basis and saying what is now in my input queue, which is actually a socket channel in Java. So how is that? What's there now? Nothing? Okay, we're going to continue to listen on a timer, but that's not available right now. And then, and we can do this as needed, but then what if we introduce as part of this a reactive stream? So we're going to have a stream that when that response message arrives at this non-blocking client, when it sees by checking the channel that now something has responded, how do we delegate that or basically channel that to the component internally that actually needed that? Well, we can then use a stream and we can offload that request, or I should say a response type, to the stream. And that stream can now have various subscribers on the inside of the bounded context. And we can do that as well. In fact, it could be that that what this represents here is actually a reactive streams processor, and a reactive streams processor is both a publisher and a subscriber. So it could be that the processor part of this, the subscriber part of it, listens to incoming responses that are being recognized here. In they're being seen through through the socket channel, then it can be responsible for subscribing to the channel, in essence, and giving those responses not just to one stream, but it sees the kinds of responses that are occurring, and when it sees the kind of response that's occurring, it knows which stream to publish to. So it could be that there are even multiple streams here, and it is sending responses through multiple streams, and those streams can even know how to translate or reify the incoming response to some sort of message that gets delivered to a subscriber inside the application. So the idea is that you may not be able to prevent blocking throughout the system. And it's very unlikely that that will ever work well if you continue to have to use a big ball of mud legacy system. And so what you can do is, in the newer software, prevent being actually tied to this kind of limitation where blocking is the case, and so you keep the newer bounded contexts so that they aren't subject to the blocking paradigm, and the threads are fully used as they're available. And even basically attempting a socket read, a socket channel read periodically is still non-blocking, because the channel reader will only read something from the channel if it's available and not block in between that. And it surrenders the thread, whether it reads a response or whether it doesn't read a response. It surrenders its thread after that processing is done. Okay, so let me break down now the reactive streams part of this a bit more, because I've spoken about some concepts of reactive streams, but I haven't gone into any detail. Okay, so within reactive streams, there are three major concepts. One of them is called a publisher, and one is called a subscriber, and one is called a publisher. And you're thinking, okay, big deal. We've been using PubSub forever. What's so great about this? Well, first of all, let me just explain again what a processor is. A processor is both a publisher, right? So it implements the publisher and it implements the subscriber interface. But for it to be an effective publisher, it really has to be, sort of a subscriber to something else. So we're going to see a stream incoming like this to the subscriber, part of the processor, okay? And then the processor does something with that incoming stream and then publishes it to one or more subscribers on this side. So we have to show that there is at least one subscriber over here that it is publishing to. And it could be several subscribers as well. So, so this is, the streams that are incoming. Hey, let's use a nice stream color like blue. Oh, don't tell me that didn't work. Okay, so, well, suddenly my clicks aren't working. Okay, so you see how the stream flows in this case with a processor. Now, what's different about reactive streams and a normal, traditional pub sub is the notion of what's called back pressure. So when a publisher publishes a stream of elements and a subscriber subscribes to that, the subscriber tells the publisher, I can accept up to 10 elements right now. So if you want to send to me 10 elements, I can deal with that. But I don't want any more. And thus, the publisher will publish to this specific subscriber by saying send. It's going to send 10 elements to it. And let's just say that this is a 4 each. Okay. It's 4 in an iterator. I'm not trying to be too fancy here. I'm just trying to show you that we're going to dispatch however many elements there are that can be accepted. Now, the next time that the subscriber receives those 10, it said, oh, I dealt with those pretty well. That didn't take long. Give me 50 next time. And so the publisher will then send 50 different elements when they are available to the subscriber. And what if the subscriber says, ooh, that was a little bit too much, right? So this is kind of like, Goldilocks and the Three Bears. I guess some Europeans aren't familiar with that story, but the story goes that a baby bear, that Goldilocks shows up at the home of the Three Bears, and she finds that Papa Bear's chair is too big and Baby Bear's chair is too little, but Mama Bear's chair is just right. And so, through time, maybe our subscriber says, oh, I can handle, it appears that I can handle on a steady basis 35 different messages. So I'm just going to lock in. And every time that I have received those 35 messages, I'm going to tell the publisher again that I will accept 35 more. So that's just one way of doing that. You may also measure ahead of time and not have to kind of zero in. So this may actually represent a test kind of environment, which would actually be more of maybe a unit test. A integration test, because you're probably going to have to introduce some sort of slowness on one side or the other. And typically, let's say that if some subscriber along the line is writing to a database, it could be that it can only write, some, number of dozens of translated elements into the database. And that could be anywhere, depending on the kind of database. That could be 35, or it could be 3,500, or it could be 35,000 per second. And, that's just up to what it actually proves to be, depending on what our stream looks like. And by the way, if you're using Aeron for one of these subscribers, or, Aeron is probably, at least not from the database side, but Aeron could give you, maybe 10 million message per second throughput, if that's what you could handle. Okay, so now we've got this idea of both a publisher and a subscriber and a processor, which is first a subscriber and also a publisher, and what it receives from this, as a subscriber, it is going to push to subscribers of its own stream, right? To its own stream subscribers, this, okay? Good. So we're pretty close to the end of an hour, and I don't mind sticking around for Q&A, but I just wanted to mention that on the DDD side of things, if we are getting some sort of stream of data, as in HTTP responses, that would, and I used this term before, that would potentially corrupt our domain model here, our ubiquitous language, if we were to take those responses in just as they are. So what we want to do is not only have a socket reader here and a processor that is subscribing to those, but it could be that the processor is also responsible for acting as an anti-corruption layer, which is a pattern of domain-driven design context mapping that says, we're not going to permit that no, hang on. Yeah. So we're not going to permit this, corrupting language or number of languages here into corrupting our domain model. So we're going to anti-corrupt the incoming responses, and then we will send them through our subscribers over here based on the partitioning that we have here, which means that each subscriber and publisher, for that matter, has the ability to transform the stream that's incoming. So say that these are let me see here. These are just simple HTTP responses that are, anemic and cruddy and all that stuff. But internally, we have in a processor what's basically a filter or a mapper of some kind, and you can have any number of those different kinds of components with it. And so the ACL will be that kind of, we could say filter and or mapper here. And when I say filter mapper, I'm talking, it could be a functional kind of filter or a mapper, like flat map or map from one type to another type, okay? So there's that. And the anti-corruption layer lives here, and we could also have the same kind of situation on this side here, where this is a processor that translates and then feeds to stream subscribers, internally, okay? So I hope that gave you a nice overview of what reactive streams do for you. And this back pressure notion really does set reactive streams apart from other kinds of publish, subscribe, and we we can benefit greatly from it. What I want to mention is that all of these concepts and components are available through my open source platform, and the platform is called Zoom. The company is Vlingo, and you can look into this, and there is a Vlingo Zoom streams support for reactive streams. You can find the open source code at github.com/Vlingo. And that's the Java source code. It's the Java open source. Okay. And our website is at https://vlingo.io. You can read about and try out the Zoom platform SDK. And I just want to mention too that there's this really powerful concept that we have that helps you get bootstrapped with domain-driven design and reactive simultaneously, and it's called the Vlingo Zoom Designer. And the Vlingo Zoom Designer uses the approach of event storming. So if you like to do event storming, pardon me, you can take the results of an event storming even design level session, and you can then, right, so we have these actions that are occurring across a timeline, and say that you have, some number of entities or aggregates, DDD kinds of aggregates, that are receiving commands and emitting events, and this happens repeatedly over a timeline. What you can do with this in Designer is you can take these all from the timeline, and not that you want to destroy the timeline, that's still important, but you can consolidate these on another surface and say, okay, this command is received by this aggregate and it emits this event. Oh, and elsewhere in the timeline, this aggregate also can receive this command, and as a result of that, it emits this event. And so you can stack these in a single place, which is kind of a crossbreed of not really a UML model, but we do use some of the UML element look and feel just to make things clear, like the state compartment and the operations department or compartment. And then through this, you can declare your Maven interface, your aggregates, and any number of these, including with value objects. So any aggregate can have any number of value objects associated with it. And then you choose your persistence. So when you choose your persistence, you can say, well, I want a journal or event sourcing, and I want to use CQRS along with that. Okay, and then you can, so this is, your database persistence option, and then you can choose your deployment, which is either native, which is just jar, or Docker, or Kubernetes. And then you get to this sort of last step. I'm kind of drawing this backwards here because it's really in this order. Right? So you design your aggregates. And then over here, you have the opportunity to generate. And what you get out of this is a completely bug-free microservice or application, depending on the scope of your bounded context, how you view it. And it's completely bug-free. You have a ports and adapters architecture. You have an event-driven architecture, and both of these are compressed. So I'm just going to highlight here that it's a compressed architecture, which means that there are only 2 layers that you have to understand. And part of this that is very important is that we support something called auto dispatch, which is optional, but it means that any incoming REST request or any incoming event from a message broker or bus is automatically translated into a command, one of these commands, and sent as a message to the domain model inside. Okay. And that means there's no application services, so you cut out an entire layer. All persistence is handled automatically for you. You don't even need to think about it. And all that you have to put in here is additional business logic, because when you generate this, it's actually built for you by the Zoom designer through Maven. You can literally just go start the server. It's a single node grid cluster, and start hitting it with curl requests or Postman or whatever it is you like to use, and you've got a lot of a huge head start. You have an unfair advantage over most of the industry, because if you've ever built these things before, I think you'll admit that it was fun, like learning that the first time, because you didn't understand how to do it and you really wanted to learn it. But maybe the second time you did it, you went, wow, this isn't so fun after all, right? Boy, I wish there was another way to just not have to keep track of, building all of these events from scratch, doing all this stuff, oh, did I forget to enter to create an event type, right? Or anything like that. And also there's a natural integration to our schema registry, Vlingo's Zoom schemata. So you have an automatic integration point for multiple bounded contexts, DDD bounded contexts, to depend on the events from other bounded contexts. Schemata basically enables the DDD published language pattern. It's clean, it's versioned, it's multi-programming language, and so anything that is published as a, let's say, an event type up to schemata from here can be drawn down to another, or so this is basically like Git, it's called a push, and this is called a pull from the registry, and now we get source code auto-generated for our local environment based on the language that we're using, and even versioned. So and the push up here is a version protected compatibility protected push, so you can't create a breaking change under any given situation, only if the semantic versioning of this allows it. So what we've created for you is really, really incredibly convenient, powerful, again, giving you a big head start and competitive advantage over others, gives you an unfair advantage. So take a look at this. It's free. Download it, use it. We build snapshots every day. Keep up with our snapshots. Subscribe to support. We currently, and I can promise you, this is the last week of $30 a month support for developer support. If you don't get that, the prices are going up significantly starting next week. So just be aware of that. So anyway, I'd be glad to take your questions now. I hope this was all helpful to you.
Okay, guys. So let's move to the next part, question and answer. We have a few questions on our chat. So let's start from first question from Tomasz Borek. And the question is, what would you say are key differences in Smalltalk OOP messaging passing and Java OOP messaging passing via method invocation?
Well, it's, the main differences are that the compiler compiles out the overhead that used to exist or still does exist with Smalltalk, although I think Smalltalk now does dispatching more intelligently. But yeah, so when you send a message, when an object, let's see here, when an object sends a message to another object here in Smalltalk, it's like I said, this do something, the name do something, and the fact that it takes 0 parameters would be used as a key in what is basically a hash table or a hash map. And we can just call this string today. Back in the Smalltalk days, this was called a selector. And a selector was basically a string, but there was, anyway, there was a special characteristic of that selector. And so you have this map here, and let's just call it message to method. That's not what it was called. I think it was just called methods or instance methods, because there are 2 kinds of methods in Smalltalk. Yeah, so Smalltalk would look up using this message selector, the method for that, and when it got the method instance, I think the name of the message was called invoke, and it would say invoke, and then somehow you passed invoke, maybe it was invoke with, and then arg and arg, however many arguments there were. Well, we know that now Java just basically takes the concepts of object-oriented and compiles them out into an optimized direct dispatch onto a method. So, they're quite a bit different internally, but you can still think of this in Java as a message that is sent to an object.
Okay, I think that's conclude the subject, the question. Let's move to the next question, and it would be, what would be your book recommendation for reactive programming?
Use Zoom Designer. you really get like a huge head start, where the only thing that you have to think about in Zoom, if you use our auto dispatch feature, the benefit is you don't have to write this layer of things. Like if this is an HTTP right, request handler, you don't have to write that yourself. And if this is a Rabbit MQ listener, you don't have to write that yourself. We do that for you, and it's very simple. And then the only thing you really have to do is, if you even need to, is go into the domain model, and you have some domain model objects. And let's say that you have, you've said, well, we're going to use event sourcing. All of this is automatically created for you, and your events will be automatically persisted, okay, out to the journal. And inside, there is no knowledge of persistence inside a domain object. Everything is business oriented, and the interface for how something gets persisted is called apply. So you apply an event to yourself. Behind the scenes, there is an atomic persistence happening, and then this event will be reflected after the persistence is guaranteed as completed and committed to the database. Then the state of this object is transitioned, and the actor remains in memory. This object remains in memory until it has to be flushed from memory. And then part of the ecosystem recognizes that not only have you asked for a journal for event sourcing, you also, if you're using CQRS, these events are automatically, after persisted here, are automatically dispatched to projections here on this side, and the projections are pre-built for you for the basic domain model that you've described, and then the projections project automatically your view state, right, your query model into the query model database. Okay, so again, the only thing you have to think about is your domain model objects. Then, so this we call this a low-code solution, but don't let low-code scare you. This doesn't mean that you can't touch the, like you're deep in some framework and, oh man, that's all binary and we get to that. It's hosted on the cloud somewhere and we can't get to that, like Mendix thing or whatever. No, you have access to all of this source code. It's all yours, and you can take it over and fork from that. But the beauty of this learning process is also that you don't have to deal with this up front. And when you use this, you won't even realize that you're using reactive. You will start to realize that you're using reactive if you start working in these areas here. And in fact, this one, you don't even need to work in the journal itself. The journal object here is, you don't have to touch that, although you could write to the journal directly if you wanted to, but that doesn't really make a lot of sense. And let me point out one other thing. I have this new book called reactive domain-driven design. And it's a free book that you can download from our company website. And let me give you the and this teaches reactive from the ground up, teaches DDD and how these fit together. And let me see here, Kalele. So if you go to Kalele, oops, way back here. Where am I? Oh, yeah. So if you go here, you can get the free book.
Okay, I think also let's conclude our topic about that. Let's move to the last questions, but it's not the one question, but a few of them from Tomasz Maciejewski. And how does DDD fit to the stream processing? Is the stream notion only for the communication between bounded context? And the last one, what is the relation of the reactive DDD with stream to architectures like Lambda or Kappa?
Okay. Wow. Can we take one of those at a time? That's like three questions in one. So what was the first one again?
How does DDD fits to the stream processing?
It fits very well. I mean, you know, there's actually a lot of streaming going on in this kind of solution. It may not be obvious to you, but actually the journal dispatching is essentially through a stream. And so, you know, there's a lot going on here, but streaming with DDD, it can be used in any way that's necessary. So if you are a subscriber in the domain model, for example, then each of the elements that you receive can be used to send messages into the domain model actors. I think it fits very well. And, you know, I don't know exactly what you're looking for in an answer, but I would say that's, you know, kind of what I would say about it. What was the next question?
Yeah, next one would be is the stream notion only for the communication between bounded context?
No, inside as well.
Okay. And the last one, what is the relation of reactive DDD with streams to architectures like Lambda or Kappa?
Kafka?
Kappa.
Kappa. Can you remind me what that stands for?
This is like some of the architecture about the streams, I think, messages, events.
Wow. Okay. There's so much terminology. I think I have heard of it and even read about it, but right now it's slipping my mind. As far as Lambda goes, if you mean like Cloud Lambda, well, Cloud Lambda is an event-oriented, you know, kind of platform, because when you create a Lambda, you have to tell AWS, for example, if I'm assuming you're talking about AWS Lambda, you have to tell AWS what kinds of events do I receive, right? So when something happens, whether it's a flow from a stream internally in your system or an HTTP request from the outside, those are all handled as events and in essence routed and streamed to you. So I would say that it's much, you know, like this kind of situation where you see, in this case, it would be like an HTTP request, and that HTTP request would be, you know, then and this would be part of the AWS, platform. But then let's say that somewhere in here, this is a Lambda, or you could actually say that this entire bounded context is a Lambda, because your Lambdas don't have to be just one entity. For example, it could be, a small bounded context, as long as it's underneath the memory, total memory size of a Lambda. Yeah, and the same thing would apply for Google Cloud Platform functions, and I think Azure also calls them functions. So yeah. I won't take time to look up COPA right now, but I'll be sure and do that after this.
I think that's conclude our Q&A section. Thank you all for the questions. And thank you, Vernon. Thank you, Vaughn, for having this presentation for us. Thank you all for the participant in this meeting. And let's see when the pandemic will end. Let's try to meet together.
Yeah. And I should tell you too that three of our teammates on Vlingo Zoom are from Poland. So one, Tomasz Jaskula, is from Poznan. Kuba Zalis is, I think he's from Gdansk, and also there's another Kuba, another Jacob, and he's I think he's from Krakow. Yeah. So.
Okay.
Yeah.
So once again, thank you all. I hope you enjoyed.
Yeah.
And see you for the next meetup.
Okay. Take care. Bye.